Module 6 is an overview of Lean tools. Part 1, we're going to have an introduction and then a discussion of push versus pull systems. Here's an overview of what we're going to cover in Module 6. Part 1 is our introduction and a discussion of push versus pull systems. Part 2 is Kaizen, which is continuous improvement. Part 3 is 5S, which is devoted to tools for getting organized. Part 4 is the theory of constraints, made famous by Goldratt in his book, The Goal. Part 5 is about value stream mapping, a very popular tool used today. And Part 6 is devoted to a specific look at the Toyoto Production System and its impact on the world of Lean. It was mentioned several times already that we're including Lean in this program, even though it wasn't in the original Motorola version of Six Sigma. I think the evolution of Sigma justifies Lean being an integral part of it. So Lean is devoted primarily with eliminating waste and non-value-added activity and has a huge impact on reducing inventory. Six Sigma, the traditional sense, is devoted to reducing variation and meeting specifications, although it could be argued very strongly that this includes reducing waste. There have been minor controversies early on about which was a better approach to use, but I think quality professionals generally agree today that both are essential and that they go together. This slide was used earlier in the program. It's used again here to give some context. Sometimes companies that are early in their journey have products and processes where they have a high scrap rate. They have processes that are out of control and not capable. And they're really at a loss for how to reduce them in an organized way. These problems are huge, and they need to be attacked first before you start getting into more sophisticated Six Sigma activities. So Lean activities like Lean, Kaizen, theory of constraints, where you're attacking bottlenecks, where you're eliminating inventory, cutting down on non-value-added activity. This is the low-hanging fruit. So there's nothing wrong with getting started with this journey at the very beginning of your move up the 6 levels of quality system implementation. Emphasizing again that lower level companies might not be ready to adopt Six Sigma full on. Lean is very effective in getting certain problems eliminated and starting to create the culture that you need for using more advanced tools. So you can get dramatic savings early on with Lean. The danger, I think, though, in this preparation is if you take some of the tools and call them a Lean program, you may be short-sighted and short-changing what needs to come on later on. What is Lean? Well, Lean, first of all, is a philosophy. The philosophy is based on Lean principles, and we'll look at Toyota's 14 principles. It's dedicated to eliminating wastes and also to the concept of understanding value-added versus non-value-added activity. What's nice is once you create a Lean thinking culture, people recognize right away when something is non-value-added, and they can eliminate non-value-added activities before they're even implemented. But Lean does require a culture based on trust, encouragement, and appreciation of employees' ideas and of competent, motivated employees. Lean is the use of a variety of tools to reduce non-value-added time and effort from your organization, to eliminate waste. Now here's a list of the tools, and there are probably more, but these are very commonly used as part of an overall Lean program. Some companies start with value stream maps and then they use that as a starting point. But you can use the tools in a discrete way depending on what your particular situation is or what your problem is. Some of these will be discussed in more detail throughout the module. In any conversation about lean, it's essential that we first define what a push versus pull system is. A push system refers to the practice of building to stock, and that's very common in many organizations. I know when I worked at General Motors, I would characterize us at that time as a push system. We were building to stock so that people could buy out of inventory. A raw materials inventory that's part of a push system is where you keep a huge supply of raw materials around so that you can schedule anything you want without delay. But it requires having a large raw materials inventory. Work in process inventory in a push system consists of a lot of buffers and safety stocks so that you have room to accumulate if you need to, and you have material to draw from if somebody before you in the system breaks down. This requires excess inventory to fill the buffers. And finally, in a push system where you're selling from stock, you have to create that finished goods inventory so orders can be filled without delay. So this is what a push system is. It's inventory driven. Typically though, you do some kind of forecasting to try and estimate what customers are going to need and then base how much inventory you're going to have on that. But the whole push system relies on having adequate inventory so that you can order or fill orders at will. A pull system, on the other hand, refers to the practice of not starting production until an order has been placed. So once an order is placed, it triggers the obtaining of raw materials and the beginning of production. Material is ordered to arrive just as it's needed, and that greatly reduces the need for raw materials. It also reduces work in process inventory, and you reduce finished goods inventory because theoretically, as soon as the product is completed, it would be shipped. This goes back to the old just-in-time concept. Now, since goods are built to order, large finished goods inventory, work in process inventory, and raw materials inventory is not needed. Let's look at some of the managerial issues concerning push versus pull systems. The first one that we're going to talk about is economic order quantity. The EOQ is the size of a batch that you would produce in order to minimize your overall cost of setup so that we spread that out economically over the number of parts that we're going to use. But this generates inventory because we might be building large batch sizes in order to get the economic best size. If we could reduce or eliminate the setup time and the setup costs, we could lower the EOQ. So just in time or a pull system for reducing inventories would depend on being able to cut down your setup times so that you don't have to have high inventories to get economic production sizes. Some tools used for this are flexible manufacturing, SMED, which stands for single minute exchange of die, cellular manufacturing, or other methods that can virtually eliminate setup time. Another managerial issue is buffers or safety stock. This is the inventory we keep between departments to insulate them from each other so that they can maintain production in case of a breakdown. This increases work in process inventory. Another purpose for buffers is if we have some scrapped parts, we have some extras around so we can meet our quotas and fill the customer's orders. I remember when I worked at General Motors, managers used to fight to have buffers because they wanted to stay out of trouble, from either starving the department downstream from them or being starved by the department upstream from them. Inventory cost is another aspect of this. It's been implied all along. But what is it about inventory that we don't like? Well, first of all, inventory is a cost that doesn't get us anything. Our money is tied up. It's not making a return. It's not an expense, so we can't subtract it from our revenue in order to protect us from paying taxes. It can't be used for anything other than taking up floor space, adding cost for rent, increased utilities for insurance, security cost to guard it, and handling cost. Also, inventory is subject to shrinkage from loss, damage, misuse, theft, obsolescence. So there's nothing good about inventory unless it's helping you save money some other way. But most companies are finding that eliminating inventory or reducing it to an absolute minimum is a strategic initiative. So let's look at an example of a pull system. KanBan is one of the earlier versions of a pull system. It's a Japanese method. The word KanBan means card signal. In other words, when an order is placed, a card is generated that says it's time to begin filling an order. And so an order only gets started when there's a card generated, and the only time that you do anything is if there's a card asking you to do it. So in essence, the product is pulled through the system and there's no extra inventory, and this reduces our overall cost. This is commonly used within the automobile industry, and there are other industries that are working harder and harder to get to where they have a flow that follows this KanBan approach. Let's take a final look at KanBan and some of the implications. First of all, when we say we're not going to do anything until we have a KanBan, what we're saying is we don't want to spend any money on raw materials or processing until we have an order. So we're trying to reduce cost and waste that way. We're also extending that to suppliers. And we're saying that we don't want them to send us any product unless we have an order that we're going to use to fill it with. So nothing happens without a KanBan. So that's an effort basically to reduce waste. But also it extends to wanting to not produce defective parts because that can mess up our counts. And we only want to produce what we're going to fill for an order. So it's important that we watch our correct amounts and that we only ship what the order calls for from one step to the next in the process. Now this can be problematic because you don't want to not be able to fill an order because of an excessive amount of scrap. In order to do KanBan effectively, you have to fix problems and get to the point where you have very few defects. This was a problem with the just-in-time approach. They really weren't able to produce parts in those smaller amounts because of the amount of scrap they had. So we want to reduce the number of KanBans, and we want to control our inventories, and also if we find problems we need to get them fixed. Well, let's add another comment or two to this and talk about the bigger picture. What we're really talking about here is trying to have the absolute minimum number of parts in our system that we possibly can. The implication there is that the ideal system would be one-piece flow. In other words, when an order comes in for 1 part or 10 parts or 100 parts, instead of producing them in batches, we're producing them one part at a time through the system, which would ultimately reduce our inventory to an absolute minimum. So one of the movements that's going on right now is to try and achieve one part flow and get away from batches. It's really kind of remarkable when you see some of the one-piece systems that have been put into place. So anyway, we're going to wrap up with that. And thank you very much. We're moving on.